Alright, how's everybody doing this afternoon? I am Tyler Theriot. I am in a group with Austin Burke and Sam Staggs, and next week we'll be doing the Clapeyron experiment, so I'll be giving a lead presentation for that today. So the objective of this experiment overall is to determine the latent heat of vaporization of water over a range of different temperatures and pressures, and we'll do this by using the Clapeyron equation to get different latent heat of vaporization values, and we'll also verify those results using steam tables that you can find in your thermo textbook. A little bit of background about this. The Clapeyron equation represents a relation between saturation pressure and temperature, as well as the change of enthalpy in a system and the specific volumes. This Clapeyron equation is an example of how enthalpy can be determined from different pressure and temperature measurements in whatever system you'll be taking those measurements in. A little bit of theory. So this equation is the Clapeyron equation. The left three are the regular equation, and then on the right, that HFG P sat over T squared R is the same equation looking into ideal gas laws and variables. So Psat is a saturation pressure, T is a saturation temperature, SFG is the specific entropy, HFG is the latent heat of vaporization, that's what we'll be calculating. VFG is the specific volume of the system, and R is the ideal gas constant. So the apparatus is set up, as you can see in this picture on the right. It's got a 1 liter flask that's filled up with about 2 inches of water. Then that sits on a hot plate heater that'll heat the water and the beaker. There's also a type K thermocouple that'll be used to take the temperature measurements. There's a analog pressure transducer that is from 0 to 15 psia. For reference, 14.7 is standard atmospheric pressure, so this system, or specifically this transducer, will be reading vacuum volume values. Has a 9-volt power supply. There's also a mechanical pressure gauge that'll be, there's a pressure gauge that comes from the transducer, sorry. There's an air bleed valve that's used for the system to ensure that any unwanted air can be bled out. There's a vacuum control valve, a centrifugal pump that'll be in vacuum, a water reservoir, which is kind of like an aquarium for this, and there's a data acquisition system on the computer that'll get the values from the transducer. So some experimental goals we have. So ultimately, we want to prepare a pressure versus temperature plot that's using our experimental data and values, and we'll compare the experimental data on the same graph as our steam table values, as our theoretical. We'll also calculate the latent heat of vaporization values H using the experimental data from the Clapeyron equation in 3 different procedures. So at first we'll approximate the value as a function of the ideal gas constant, saturation temperature and pressure, as well as differential pressure over differential temperature. Then we'll determine an expression to estimate the latent heat of vaporization as a function of temperature, as well as predicting the pressure and differential pressure over the entire temperature range as a function of temperature. But overall, our goal is to adopt a visual understanding of the water changing states as the temperature and pressure inputs change. So the procedure for this, we'll set up the data acquisition system, ensure that the thermocouple and the transducer values are showing on it. Then we'll set up the experimental apparatus. We'll fill the beaker with 2 inches of water just about. We'll also do a leak test to make sure that the entire system isn't leaking water as it would get pretty hot. We'll then turn on the vacuum pump and bring the flask to its lowest vacuum. And then once we have it there, we'll plug in the hot plate, set it to high to get that water boiling. And we then need to confirm that the thermocouple is submerged in the water, but it's not touching the beaker or boiling beads. Boiling beads could be added. That'll be decided as we do the experiment. We'll then begin logging the data once the water starts to boil, slowly closing off the vacuum line to build pressure and get it closer to that 14.7 psia value. But right before it gets there, we're going to open that bleed valve to ensure that the entire system is under vacuum and it's not creating any positive pressure. We'll then stop taking data once the water gets to a rolling boil, or a vicious boil, a lot of people call it. And then once we stop taking data, we'll turn off the hot plate and allow the beaker and the water to cool off. So some of the anticipated results. This is data from the steam table showing a pressure over a range of temperature from 0 to 100 degrees Celsius. It kind of follows a gradual curve, and that's what we're expecting for the results that we will take. And some values that we have for the latent heat of vaporization at 3 different arbitrary points. So at 10 degrees Celsius, it's 2,519 kilojoules per kilogram. At 50 degrees C, it's 2,591 kilojoules per kilogram. At 100 degrees Celsius, it'd be 2,676 kilojoules per kilogram. So those values will kind of be a little more linear over the range of temperature, and that's kind of what we're expecting as we perform the experiment. So going over some safety for this lab, you must wear your closed-toe shoes and your safety glasses like most labs, as well as long pants, but there's a slip hazard there. If any water gets on the ground, you don't want to slip, and a burn hazard because we'll have a hot plate, hot beaker, and hot water. These are my references. Are there any questions? All right, thank you very much.